Welcome! In this session, we'll be tackling LeetCode problem number 538, convert BST to greater tree. This is an interesting tree transformation problem that highlights the properties of binary search trees and how we can manipulate them to solve practical challenges. Let's dive in and explore the problem and its solution step by step. In this problem, we are tasked with converting a binary search tree, or BST, into what's called a greater tree. The transformation involves modifying each node's value so that it becomes equal to its original value plus the sum of all keys in the BST that are greater than it. The input to the problem is the root of the BST, where each node has a value, and potentially left and right child nodes. The output is the root of the modified tree, with all the node values updated according to this rule. Here, we have an example to better understand the transformation. The original BST is shown on the left, and the resulting greater tree is on the right. Notice how each node's value changes. For instance, the leaf node with the value 8 remains 8, since there are no greater values. On the other hand, the node with value 7 becomes 15 after adding 8 to it. Similarly, the root node 4 becomes 30, as its new value accounts for all the nodes with values greater than 4. This process is applied recursively throughout the tree, ensuring that every node is updated correctly based on the same principle. Continuing with the explanation, the transformation also updates the smallest values in the BST. For example, node 0 becomes 36 by adding the values of all other nodes in the tree. This ensures the transformation is applied consistently across every node. A smaller example is provided next. In this case, we have a BST with just two nodes, 0 and 1. After the transformation, the tree becomes a greater tree, where node 1 remains unchanged because it has no greater values, and node 0 is updated to 1, which is the sum of 0 and 1. Now let's look at another example with a different structure. Here, the BST has two nodes, where 2 is the root, and 0 is its left child. After converting this to a greater tree, the root node 2 remains the same since there are no greater values than 2. The left child node 0 is updated to 2, which comes from adding its original value of 0 to the value of the root node 2. This example highlights that the transformation works regardless of the structure of the BST, whether it is left-skewed, right-skewed, or balanced. Finally, let's review some important constraints and edge cases. The number of nodes in the BST can range from 0 to 10,000, so the solution must be efficient enough to handle large trees. Node values can range from -10,000 to 10,000. And since all values in the BST are unique, there's no risk of duplicates complicating the transformation. In edge cases such as an empty tree, the output should also be null. For a single node tree, the value remains unchanged. Additionally, the solution must handle unbalanced trees and negative values correctly, ensuring the transformation applies universally across all valid inputs. To solve the problem of converting a binary search tree into a greater tree, the goal is to update each node's value so that it becomes the sum of its original value plus the values of all nodes that are greater than it. Leveraging the properties of a BST, where the right subtree contains larger values, we considered several approaches. First, the brute force approach involves traversing the entire tree for each node to calculate the sum of all greater values. This is done by performing an in-order traversal to access each node, and then for each node, a separate traversal is performed to find and sum the values greater than its current value. However, this approach is highly inefficient, with a time complexity of O(n squared), as every node triggers a full traversal of the tree. It also uses O(h) space for the recursion stack, where h is the height of the tree. While conceptually simple, the repetitive work makes this method impractical for large trees. Alternatively, the optimized approach uses reverse in-order traversal, which processes nodes in descending order, starting from the largest value. This avoids redundant calculations and significantly improves efficiency. In the optimized reverse in-order traversal approach, we maintain a running sum initialized to 0. As we traverse the tree in reverse in order, starting with the rightmost node, then the root, and finally the left subtree, we add the running sum to the current node's value and update the running sum with the new value. This ensures that the running sum consistently reflects the accumulated total of all nodes greater than the current one. As a result, we only traverse the tree once, giving this approach a time complexity of O(n). The space complexity remains O(h), as the recursion stack depends on the height of the tree. This method is efficient because it avoids recalculating sums and leverages the BST's inherent structure. Additionally, an iterative alternative to this approach uses an explicit stack to perform the reverse in-order traversal. While it mirrors the recursive method's logic and maintains the same time and space complexities, it requires manual stack management, which can add to implementation complexity. Both the recursive and iterative versions are efficient, but the recursive variant is often favored for its simplicity and clarity. Given the options, the optimized reverse in-order traversal, particularly the recursive implementation, stands out as the most effective strategy. It is both straightforward to implement and highly efficient, as it leverages the natural order of the BST to eliminate redundant computations. The key insight is that reverse in-order traversal visits nodes in descending order, aligning perfectly with the requirement to calculate the sum of all greater nodes. By maintaining a running sum, we completely avoid the inefficiencies of the brute force approach, which recalculates sums for every node. While the iterative method also avoids redundancy, it introduces the complexity of managing an explicit stack. The recursive approach, on the other hand, is elegant and easy to follow, making it the optimal choice for this problem. It strikes the right balance between efficiency and simplicity, making it well-suited for both conceptual understanding and practical implementation. In conclusion, the recursive reverse in-order traversal effectively addresses the problem requirements and demonstrates the power of exploiting the BST's inherent properties. The problem we're solving here is to transform a binary search tree, or BST, into a greater tree. The transformation involves updating each node's value to be the sum of its original value plus the values of all nodes that are greater than it. Importantly, the structure of the BST must remain intact. To achieve this, we take advantage of the properties of a BST, where all nodes in the right subtree are greater than the current node and all nodes in the left subtree are smaller. By performing a reverse in-order traversal, visiting nodes in the order of right, root, and then left, we can process nodes in descending order of their values. During this traversal, we maintain a running cumulative sum that represents the total of all greater node values encountered so far. Each node's value is updated to this cumulative sum as we go. This approach allows us to modify the tree in place, avoiding the need for extra memory to store the transformed values elsewhere. To implement this transformation, we start by defining a recursive helper function called convert that takes the current node as input. The function modifies the node's value in place while updating a running total, stored in a variable called cumulative_sum. The base case for this function is straightforward. If the current node is null, we simply return without doing any work. For the recursive step, we first traverse the right subtree, which contains the larger values. After processing the right subtree, we update the cumulative sum by adding the current node's value to it, and then replace the node's value with the updated cumulative sum. Finally, we traverse the left subtree, which contains the smaller values. Once this recursive process is set up, we initiate the transformation by calling convert on the root of the tree. When the recursion completes, the entire BST will have been modified into a greater tree. Throughout this process, we're only using the BST itself and a single variable for the cumulative sum, making the solution efficient and memory-friendly. The key operation here is the reverse in-order traversal, which ensures that nodes are visited in descending order of their values. Starting from the rightmost node, which holds the largest value, we work our way back to the root and then to the left subtree, progressively updating the cumulative sum and the node values. This traversal is crucial because it aligns perfectly with the requirements of the problem. Another important aspect is that this transformation is done in place, meaning we directly update the node values as we traverse, without creating additional data structures. When analyzing the complexity, the algorithm is very efficient. The time complexity is O(n), where n is the number of nodes in the tree, since we visit each node exactly once. The space complexity is determined by the recursion stack, which depends on the height of the tree. For a balanced tree, this height is O log n, while for a skewed tree, it could be as much as O(n). This approach ensures that the solution works efficiently for both balanced and unbalanced trees. The accompanying code implementation begins by defining the treenode class and the main function convertBST. Inside this function, we initialize the cumulative sum to 0 and then define the recursive helper function convert. The recursive function convert starts by checking if the current node is null. If it is, there's nothing to process, so we return immediately. Otherwise, we begin by traversing the right subtree, which contains the greater values. After completing the traversal of the right subtree, we update the cumulative sum by adding the current node's value to it. We then replace the current node's value with this updated sum, effectively transforming the node. Finally, we move on to traverse the left subtree, which contains the smaller values. By following this sequence, right subtree, current node, left subtree, we ensure that the traversal respects the reverse inner order. Once the helper function is defined, we initiate the process by calling convert with the root of the tree. When the recursion finishes, the BST is fully transformed into a greater tree, and we return the modified root. This implementation also accounts for edge cases such as an empty tree, where the function should return none without any errors, and a single node tree, where the node's value remains unchanged since there are no greater values. The algorithm is robust enough to handle even skewed trees, ensuring that the traversal order remains valid regardless of the tree's shape. Additionally, the algorithm can naturally handle trees with negative values. Since the arithmetic operations for updating the cumulative sum and modifying the node values remain the same, the transformation works seamlessly even when the BST contains negative numbers. This flexibility makes the solution applicable to a wide range of input cases, ensuring correctness regardless of the values stored in the tree nodes. By combining the reverse inner traversal, in-place modification, and efficient handling of edge cases, this algorithm provides a clean and effective way to convert a BST into a greater tree. Here, we begin the Python implementation of converting a BST to a greater tree. First, we define the structure of a binary tree node with the treenode class. Each node has a value, and pointers to its left and right children, which are initially set to none. Next, we create the solution class, where the main logic resides. The convertBST function is defined, which takes the root of the binary search tree as its input. Inside this function, we initialize a variable called cumulative_sum to 0. This variable will be used to keep track of the running total of node values as we traverse the tree. To perform the conversion, we use a helper function called reverse_in_order. This function implements a reverse in-order traversal, starting with the largest values in the tree, which are found in the right subtree. If the current node is null, the function returns immediately. Otherwise, we first traverse the right subtree to process the greater values. After that, the current node's value is updated by adding it to the cumulative_sum, and the cumulative sum itself is updated to include this node's value. Finally, we traverse the left subtree, which contains the smaller values. The reverse_in_order function is then invoked, starting from the root node of the tree. This ensures that the entire tree is traversed in reverse in-order sequence, and the values of all nodes are updated to reflect the cumulative sum of values greater than or equal to them. Once the traversal is complete, the modified tree is returned as the output of the convertBST function. The result is a greater tree, where each node's value is replaced by the sum of all values greater than or equal to itself in the original tree. Here, we start by defining the structure of a binary tree node with the treenode class. Each node contains an integer value, val, and references to its left and right children. The class provides three constructors: a default constructor, one that initializes the node with a specific value, and another that initializes it with a value in child nodes. Below this, we declare the solution class, which contains the logic for converting a binary search tree into a greater tree. Inside the class, we define a private field cumulative sum initialized to 0. This variable will hold the running total as we traverse the tree. The main method, convertBST, takes the root of the tree as input and invokes the helper method reverseInOrder to perform the transformation. Finally, it returns the updated root node, which now represents the greater tree. The reverseInOrder method is where the actual transformation happens. It performs a reverse-in-order traversal of the tree, which means we process the right subtree first, then the current node, and finally the left subtree. If the current node is null, we simply return, as there's nothing to process. Otherwise, we start by recursively traversing the right subtree, which ensures we handle nodes with greater values first. Next, we update the current node's value by adding its original value to cumulative sum and storing the result back in node.val. This effectively incorporates all greater values seen so far into the current node. Finally, we move to the left subtree to process the smaller values. This approach ensures that each node is updated correctly to reflect the sum of all greater or equal values, completing the transformation of the tree. Here, we start with a simple binary search tree consisting of 3 nodes, 2 as the root, with 1 as its left child and 3 as its right child. The goal is to convert this BST into a greater tree by modifying each node's value to the sum of all values greater than or equal to it in the original tree. To achieve this, we initialize a variable cumulative_sum to 0 and perform a reverse in-order traversal, which processes nodes in descending order: right, then root, then left. First, we visit the rightmost node, which is 3. We add its value to cumulative_sum, making it 3, and then update the value of node 3 to 3. Next, we move to the root node, 2. Adding 2 to cumulative_sum gives us 5, and we update the root's value to 5. Finally, we visit the left child, node 1. Adding 1 to cumulative_sum makes it 6, and we update node 1's value to 6. This completes the transformation for this example. Now, after updating the values, the BST has been transformed into a greater tree. The updated tree has 5 as the root, with 6 as its left child and 3 as its right child. Moving on to a larger example, we have a BST with 5 as the root, 3 and 8 as its left and right children, respectively, and additional nodes, 2 and 4 as children of 3, and 10 as the right child of 8. Once again, we initialize cumulative_sum to 0 and proceed with a reverse in-order traversal. This ensures we process the nodes in descending order, starting from the rightmost node, then the root, and finally the left subtree. We begin with the right subtree, visiting node 10 first. Adding 10 to cumulative_sum makes it 10, and we update node 10's value to 10. Next, we move to node 8, adding its value to cumulative_sum, which now becomes 18. Node 8's value is updated to 18. Moving to the root node 5, we add its value to cumulative_sum, resulting in 23, and update its value to 23. For the left subtree, we start with node 4. Adding 4 to cumulative_sum gives 27, and node 4's value becomes 27. Then, we visit node 3, adding its value to cumulative_sum to get 30, and update node 3's value to 30. Finally, we visit node 2, adding its value to cumulative_sum to reach 32, and update node 2's value to 32. The updated tree now has 23 as the root, with 30 and 18 as its left and right children. The left subtree is further updated, with 32 and 27 as the children of node 30, and node 18 retains 10 as its right child. In this edge case, we examine a binary search tree consisting of just a single node, 1. Since there are no other nodes in the tree, the reverse in-order traversal simply processes this single node. We begin by initializing cumulative_sum to 0. Visiting node 1, we add its value to cumulative_sum, which becomes 1, and update the value of node 1 to 1. The tree remains structurally unchanged, but the process demonstrates that even in the simplest scenarios, the same approach applies. This highlights the consistency of the reverse in-order traversal method for converting any BST into a greater tree. To summarize, the approach relies on a reverse in-order traversal, which ensures nodes are visited in descending order of their values. A cumulative_sum variable maintains the running total of node values as they are processed, and each node's value is updated with this sum. This guarantees that all greater values are added to each node. The time complexity of this solution is O(n), as each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursive stack space used during traversal. This makes the algorithm efficient and well-suited for BST to greater tree conversions. The time complexity of our solution is O(n), where n represents the number of nodes in the binary search tree. This is because we perform a single reverse in-order traversal of the entire tree. In this traversal, the helper function visits each node exactly once. For every node, the value is accessed and updated in constant time, or O(1). Since there are n nodes in total, the traversal and updates collectively require n times O(1), which simplifies to O(n). Now, if we consider edge cases, such as an empty tree, the function terminates immediately, taking O1 time. For a tree with only one node, the function performs a single operation, still O1. As the tree grows, the traversal cost scales linearly with the number of nodes, confirming that the overall time complexity remains O(n). This linear efficiency ensures that our approach processes each node only once, making it highly effective for larger trees. The space complexity of our solution is determined by the recursion stack used during the traversal, which depends on the height of the binary search tree, denoted as h. At any point in the traversal, the maximum depth of the call stack corresponds to the tree's height. For a balanced binary search tree, the height is approximately log n, leading to a space complexity of O log n. However, in the worst-case scenario, such as a skewed tree where all nodes are aligned in a single line, the height becomes n, resulting in a worst-case space complexity of O(n). Importantly, the algorithm does not rely on any additional data structures. All computations are performed in place, directly modifying the input tree. This means no extra memory is allocated beyond the recursion stack. Hence, the overall space complexity is O(h), where h represents the height of the tree, adapting to the tree's structure. When comparing approaches, a naive or brute force solution would involve traversing each node and then performing another traversal to sum the values of all nodes greater than the current one. This nested traversal introduces an additional layer of computation, leading to a time complexity of O(n squared). Moreover, such an approach often requires extra memory to store intermediate data, further increasing space complexity. In contrast, the optimized solution leverages the inherent properties of the binary search tree. By performing a single reverse in-order traversal and maintaining a cumulative sum, it avoids redundant computations entirely. This results in a significantly improved time complexity of O(n), and minimizes space usage to O(h), with memory being limited to the recursion stack. This clear optimization demonstrates why the current solution is both faster and more memory efficient, especially for larger trees. Now, let's analyze the best, average, and worst-case scenarios for the algorithm. In the best-case scenario, where the binary search tree is perfectly balanced, the height of the tree is log n. This results in a space complexity of O log n due to the recursion stack, while the time complexity remains O(n), as every node is visited once. For the average case, which represents a semi-balanced tree with random input, the height of the tree is still proportional to log n on average, maintaining O(n) time on O log n space complexities. In the worst-case scenario, such as a completely skewed binary search tree where all nodes are aligned in a single path, the height of the tree equals n, resulting in a space complexity of O(n). Despite this, the time complexity stays linear at O(n), as the traversal continues to process each node exactly once. These cases highlight the robustness of the algorithm across different tree structures. To mathematically prove the complexity, let's first confirm the time complexity. If T(n) represents the time taken to process a tree with n nodes, the algorithm performs a reverse in-order traversal, visiting each node exactly once. For each node, the operations are constant, O(1). Therefore, the total time is n*(O1), which simplifies to O(n). For space complexity, the depth of the recursion stack reflects the tree's height, h. In a balanced binary search tree, this height is log n, leading to a space complexity of O log n. In a skewed tree, the height equals n, resulting in O(n) space. Summarizing, the time complexity is O(n), and the space complexity is O(h), where h represents the tree's height. This optimized solution is a significant improvement over naive methods, offering both time and space efficiency for converting a binary search tree to a greater tree. When solving this problem, there are some common mistakes that can trip you up. One of the most frequent errors is using the wrong traversal order. Specifically, in-order traversal processes nodes in ascending order, which doesn't work for this problem. Instead, you need reverse in-order traversal, which processes nodes in descending order. This is essential because it allows you to accumulate the sum of all greater nodes as you traverse the tree. Another common issue is modifying node values before the traversal completes. Without maintaining a cumulative sum variable, the updates can lead to incorrect results since the running total isn't preserved properly across recursive calls. Then, there's the mistake of not handling null nodes correctly. Forgetting to add base case checks can cause runtime errors like null pointer exceptions, especially in edge cases like an empty tree. Finally, be mindful of variable scope. Using local variables for the cumulative sum instead of a shared variable across recursive calls can result in the sum resetting with each function call, leading to incorrect calculations. It's equally important to test edge cases thoroughly. For instance, trees with only one node, or trees that are highly unbalanced with all nodes on one side, can reveal subtle bugs in your implementation. Ignoring these edge cases can lead to incorrect results or runtime errors. From an interview perspective, this problem isn't just about coding, it's a test of your understanding of binary search trees and your ability to reason through recursive traversal. Make sure you can clearly explain why reverse in-order traversal is the right choice. Also, pay attention to your variable names. Using descriptive names like cumulative_sum rather than something generic like sum can make your thought process clearer to the interviewer. Be prepared to discuss the space complexity of the recursive solution, which is O(h) due to the call stack, or h is the height of the tree. You should also highlight the time complexity, which is O(n), since each node is visited exactly once. If you have time, consider discussing iterative solutions and how they differ from recursion in terms of readability and stack usage. To deepen your understanding, you can explore related problems that build on similar concepts. For example, LeetCode 1038, binary search tree to greater sum tree, is a variation of this problem framed slightly differently. Practicing it can help reinforce the technique. Another useful problem is LeetCode 230, kth smallest element in a BST, which focuses on in-order traversal and is a great complementary skill to have. LeetCode 701, insert into a binary search tree, is also valuable since it helps you solidify the foundational operations of a BST, which are critical for understanding traversal-based problems. Finally, LeetCode 98, validate binary search tree, tests your understanding of BST properties and traversal, ensuring you have a strong grasp of these fundamental concepts. Now let's look at some alternative approaches and their trade-offs. The recursive approach is the most intuitive. It uses reverse in-order traversal with a cumulative sum variable to update the tree. The main advantage here is its simplicity and elegance, as it leverages the BST structure effectively. However, it does use stack space proportional to the height of the tree, which is O(h). If you want to avoid the recursive stack, you can use an iterative approach. This involves simulating reverse in-order traversal with an explicit stack. While this avoids the recursive call stack and provides better control over iteration, it's slightly more complex to implement since you have to manage the stack manually. Another advanced option is Morris traversal, which modifies the BST temporarily to achieve O(1) space complexity. This eliminates the stack overhead completely, but it's a more complex technique and might be challenging to implement or explain under time pressure during an interview. Each approach has its pros and cons, so it's helpful to understand when to use each based on the problem requirements and constraints. Great job! We've successfully solved the problem using an efficient reverse in-order traversal. Remember the key insights about leveraging BST properties and optimizing space usage. Don't forget to practice similar problems to reinforce these concepts. Thanks for joining, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!